Welcome to Robotics Beyond Boundaries, Intelligent Machines in Unpredictable Worlds. In this episode, we explore 7 groundbreaking papers in computer science and robotics, with a special focus on real-world impact, disaster response, navigation, and human-robot collaboration. Join us as we highlight the paper of the day by Yizhi Wang and colleagues, offering insights from the latest research at the frontier of AI-driven robotics. This is AI Frontiers, where research, innovation, and application come together. Did you know that the world's largest robot swarm operated entirely without GPS or external anchors? Each robot determined its location by communicating with its neighbors, much like a flock of birds coordinating in dense fog. This approach exemplifies a new era in robotics, where groups of machines adapt and thrive together, even in the absence of traditional navigation aids. The core question arises: how do these robotic systems maintain orientation and functionality amid chaos? The answer lies in collective intelligence and decentralized coordination. Robotics research is now more crucial than ever, positioned at the intersection of artificial intelligence and real-world complexity. Robots contend with unpredictable environments, ranging from disaster zones to noisy, uncertain landscapes. These machines are diverse, including wheeled, legged, and aerial platforms, each facing challenges in navigation, decision-making, and human interaction. The field of computer science and robotics, abbreviated as cs.RO, merges software intelligence with hardware resilience. Today's episode delves into breakthrough studies that bridge the gap between simulation and practical deployment, underscoring the importance of this research in addressing urgent, real-life issues. Consider robotics research as a vibrant metropolis where each neighborhood specializes in distinct tasks. Navigation Alley is dedicated to enabling robots to traverse uncertain terrains. Path Planning Park is filled with algorithms that seek optimal routes through complex environments. On Localization Lane, robots strive to determine their precise position despite sensor noise and environmental ambiguity. The city square becomes a hub for decoding ambiguous human language and intent. Robotics, as a discipline, is fundamentally collaborative, integrating intelligent algorithms with mechanical systems to achieve real-world goals. Autonomous navigation and decision-making form a central theme in current robotics research. Robots must not only move, but also determine when and how to do so effectively, especially under uncertainty. Yizhi Wang and colleagues demonstrate how deep reinforcement learning, combined with fuzzy logic, enables robots to navigate safely, akin to a cautious yet adaptive taxi driver maneuvering through a bustling city. By learning from trial and error while being guided by intuition, decision-making layers are constructed that skillfully balance innovation with operational safety. Path planning in complex environments remains a persistent challenge for both aerial and ground robots. Urban landscapes and difficult terrains demand robust algorithms. Hicham Sharit's team evaluates methods such as A*, RRT*, and particle swarm optimization, likening them to advanced navigation applications for robots. Autobong Jerome and collaborators introduce rapid kinodynamic planning tailored for car-like robots. These planners must meticulously balance safety, speed, and inherent platform constraints, much like selecting the fastest lane during peak traffic while maintaining caution. Contemporary robotics increasingly relies on advanced sensing, mapping, and multimodal understanding. Jiri Horina's research explores swarm localization without GPS, comparing it to hikers navigating in fog by communicating locally. Ali Emre Baldzi's team enhances simultaneous localization and mapping, or SLAM, using Gaussian processes to construct richer, uncertainty-aware maps. Sophie Villemur's group demonstrates how four-legged robots can classify terrain types using only proprioceptive feedback. Meanwhile, Akira Oyama's study shows robots integrating auditory, visual, and linguistic cues to clarify ambiguous, out-of-sight instructions. The result is machines capable of blending sensory inputs for human-like contextual awareness. Recent studies provide striking breakthroughs in the capabilities and resilience of robotic systems. Yiji Wang's hybrid navigation approach safeguards against unsafe maneuvers by merging learning and rule-based controls. Jiri Horina's work confirms that robot swarms exhibit increased resilience when local observations are shared, allowing compensation for individual failures. Odabong Jerome's kinodynamic planning method accelerates computation by up to 104 times, enabling real-time decisions for car-like robots. Ali Emre Balsi's uncertainty-aware mapping empowers robots to make more informed decisions by quantifying environmental ambiguity. Akira Oyama's contributions highlight robots that ask clarifying questions, mirroring collaborative human behavior in ambiguous scenarios. The paper of the day, authored by Yiji Wang and colleagues, introduces a novel framework for safe and adaptive robot navigation. Focusing on four-wheel independent steering and driving platforms, the team addresses the dichotomy between deep learning, which offers adaptability but may be reckless, and rule-based control, which is reliable but rigid. Their objective is to integrate these approaches, building a hybrid hierarchy where machine learning governs high-level planning and rule-based logic ensures operational safety. This blueprint sets a new standard for balancing intelligence and dependability in robot motion control. The proposed technical solution combines deep reinforcement learning with fuzzy logic in a hierarchical control architecture. At the top level, a deep reinforcement learning agent devises efficient navigation paths based on experience. At the lower level, a fuzzy logic controller interprets and filters these plans, ensuring every wheel operates within safe, feasible limits. Training is conducted initially in simulation, allowing extensive trial and error without physical risk. This structure is analogous to a novice driver being supervised by an experienced mentor, resulting in smooth, reliable, and robust robotic navigation in real-world conditions. Deployment of this hybrid navigation system has led to demonstrably safer robots in industrial environments. The integration of learning and rule-based control bridges the divide between simulated development and real-world operation. However, challenges remain, particularly in tuning the fuzzy logic controller, which requires significant domain expertise. The key insight is the successful fusion of adaptive learning with human-like intuition. Establishing a template for future robot controllers that prioritize both intelligence and trustworthiness. Looking ahead, robotics is poised to evolve as a balanced and adaptive discipline. The field is transitioning from rigid, rule-based systems to architectures that blend data-driven learning with foundational safety constraints. Swarm intelligence will become increasingly prevalent, with teams of robots collectively outperforming individual units. The advancement of multimodal perception will enable robots to interpret the world through a combination of sensory inputs. Enhancing their situational awareness, this progression can be visualized as a river forging new channels, adapting fluidly without overwhelming the system. In summary, the integration of hybrid and swarm-based strategies is reinforcing the reliability of robots in real-world applications. Notable contributions in this episode include those by Yiji Wang, Jiri Horina, and others, pushing the boundaries of efficiency, transparency, and human-robot interaction. Although significant progress has been made, ongoing challenges remain. The robotics community relies on the curiosity and engagement of individuals to drive further innovation. Listeners are encouraged to explore, discuss, and experiment with these developments to help shape the future of intelligent machines. This presentation was synthesized using the GPT 4.1 language model for summarization and narrative structuring. Text-to-speech synthesis was performed by OpenAI, and visual assets were created using Google Image Tools. All slide content underwent review by a human expert for accuracy and clarity. Despite these efforts, minor oversights may persist. Listeners are encouraged to consult the referenced papers for comprehensive details. Complete references are provided for further study. Subscribe to the AI Frontiers channel for weekly in-depth explorations of the latest research in artificial intelligence and robotics. Your questions and insights are highly valued. Please comment and engage with the community. Stay informed about ongoing breakthroughs and emerging trends in intelligent systems. Thank you for joining us on this journey into the future of robotics. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.